Since the talk is titled The Future of Intelligent Machines, right? What does that phrase even mean to you?
This adaptive ability that a system like us, for instance, has to use skills that it has learned, whether the skills are physical or cognitive, to solve the task at hand. The way I understood machine learning was by repeatedly learning the same thing over and over again. It's like a metaphor for deep neural networks, right? We have an existence proof of a system that works. That is this 3-pound mass of brain tissue that is sitting inside the skull. That is an absolutely general purpose machine. The first artificial neurons that were designed by people like Frank Rosenblatt in the late 1950s, they were essentially the first computational models of what biological neurons do. Our understanding of the brain has always been an inspiration for AI.
Where do you believe the frontier for researchers today is?
One would be neuromorphic hardware and figuring out how to train these things called spiking neural networks in software. If you had models that were running in hardware and were using orders of magnitude less energy, that would change the economics of the whole thing. AGI, it's a moving goalpost. One system being able to do all the possible cognitive tasks that humans do, as well as an expert in the field. We're not there yet. Whatever is the intuition you're using to say that it's not already there is exactly the intuition you will use to say that it's there. I think there is a crisis of meaning that is going to come. We find the meaning in our lives in what we do and how well we do that. Writing is what gives me meaning, like my life meaning. And I do not want to use an AI for doing something that is very meaningful to me.
I do this a lot, right? Which is having people on this stage and talking to them. This time, I actually had to prepare. And like a good student, it almost rolled back the years. So I had to go, I had to do some reading, I had to watch some videos, I had to indulge some personal curiosities to be prepared. Because, today we have the eponymous Anil Ananthaswamy as our guest. Would request all of you to give a welcome, the SPC welcome to Anil. Of all the things, he's written a lot. I'm sure a bunch of you, since this is not a regular founder talk, people who are here, they're people who are aware of the body of work. But one of the things that I felt as I was researching on you was that you're a true learner. I felt that over the years, uh, just the ability to pick up stuff and indulge your own personal curiosities, I found that completely off the charts. Right. So maybe that's where we can possibly start. Because at South Park Commons, we think of ourselves as a learning community and the entire -1 to 0 journey. Would love to hear a bit of your backstory, your personal arc. We do know that you did engineering you pursued engineering at IIT Madras. And as I was telling you earlier, you're not the first IIT Madras alum on this stage, right? We've had Tarun Hutke come in earlier. And we have some IIT Madras alums in our community as well, right? So I think bunch of interesting experiences that have led you to where you are today. But let's go back to the start, right? On what made you who you are, and then what are the experiences that have possibly shaped your worldview?
Well, first of all, thank you for having me. It's a pleasure to be here. I really had not anticipated finding so much energy in this place. So it's really a pleasure. I was just asked about what it would have been like to have something like South Park Commons when I had graduated. I'm envious that you guys have this. It's fabulous. My journey, it was very traditional in the beginning. I did my engineering at IIT Madras, which looking back was very foundational. It's hard to know that when you're going through it. And I studied electronics, did computer engineering abroad, and then actually came back to Bangalore. I started my software career in Bangalore. But these were the very early days of software in India, and I immediately got sent back to the US. Ended up in Texas. Uh, so, well, yeah, that's a different story. But I worked there for a while, moved to Silicon Valley, and then for a few years worked in Berkeley in a small company. We were building these massive distributed network management systems. We didn't realize it at the time, but we had actually built the world's first web service.
Wow.
We just didn't know it. So in fact, a lot of the people who worked in that company eventually left and joined a small startup in San Francisco called WebLogic, which today runs half the world's web servers. So, but I at that time decided that something about being a software engineer, I enjoyed it, I was good at it, but at the end of the day, I just kind of felt flat. I would come back home and not quite answer the question to myself as to why I was doing what I was doing. There was a parallel pull that I had, which was I wanted to write. I just wanted to write, and at that time I thought I would write fiction, and I would I quit my regular job, became a contractor so that I could work half time. So 6 months I would work, and then 6 months I would just take off and come back to India and pretend to be a fiction writer. So I was writing fiction. I was attempting to write fiction, and then at some point I realized that there was another thing that I loved a lot, which was science. Just reading about physics and biology, and some part of me had never put the two and two together, that these books that I used to love reading, somebody else must have written it, right? That light bulb hadn't gone off. And I eventually discovered a wonderful science writing program in California at UC Santa Cruz. It was a 1-year program, an extremely intense 1 year. So I just dropped everything, went and studied, retrained as a journalist, and that led to an internship and at New Scientist in London. Came back to the Bay Area after the internship, and for a while tried to do 2 jobs, as a software engineer and as a writer. At some point realized that I could pay my bills with writing, and that was it. So after that I've been continually writing. The entire basis for this sort of change from being software engineer to being a writer was really to satisfy this feeling of wanting to pay attention to the world. I felt like I wasn't doing that as a software engineer. I really wanted to ask sort of foundational questions of myself and of the world around me, and I felt like writing was the best way I could get at that. So almost everything I've written about, it's really not, nothing to do with technology. Much of it has been about exploring, what's happening in cosmology, what's happening in quantum mechanics, what's happening in neuroscience. So yeah.
You've I think one of the things that I'm often amazed by, right, as I was reading through your personal journey, was that just the ability to go back and learn, right, and to meaningfully explore. What in your personal journey, right, through the years, possibly made it natural that, this is a natural course of things for you, right? Because especially when I've talked to people even now, some of the topics that you've written about, right, whether it's cosmology or there's quantum mechanics, or of course the book that we're going to possibly talk about far more today, right, given the topical nature, is that people think that many of these things are complex concepts, and the complexity often scares them away into actually peering under the hood. So I'm just curious what made you go there and say that, hey, this is exactly what I want to do?
I mean, curiosity, some underlying curiosity that I can't analyze. I mean, it's there. I just, I look at something that is fascinating, and yes, it seems difficult at first, but one of the, if there is a thing that I've learned over the years, is that just persisting. In fact, I make the point in the beginning of this book about the math, is that the way I understood machine learning was by repeatedly sort of learning the same thing over and over again. It's almost like, it's like a metaphor for deep neural networks, right? I mean, you just show the thing, data over and over again, and it learns the patterns. We are no different. I think some of it is just persistence. But this is a question also that writers often ask of me, which is, how do you get better at writing? And these things are linked. I often tell the writers in the audience that if you make your ability to live and pay rent depend on your writing, you will become a good writer, right? If you are just doing it as a hobby, very unlikely that you will improve. But make your livelihood dependent on it, and you just have to get better. And then the choice of what you write about is the other axis on which you are improving. And in my case, it was just overarching curiosity about the world that we live in, and I'm often asked the question, how come these books are so different, right? Cosmology, quantum mechanics, neuroscience, now machine learning. To me, they're all parts of some larger whole, right? That I'm trying to make sense of. And so it doesn't, in my mind, they don't feel different at all. They're just explorations of big questions about, who am I? What is this universe? Why are we here? All these things. If you take those big questions and boil them down, you'll end up with these stories.
No, absolutely. Yeah, I think there is no better way to get great at anything apart from interesting constraints that come your way. One thing that I've often heard about writers is that you are what you read, right? The quality of your writing does end up reflecting your diet on what you've been reading. So I'm just curious, what is it that you read, and what are you reading right now?
Right now, and we've already talked about this offline, a lot of my reading, unfortunately, is in service of my writing. So I honestly haven't had the privilege or time to read for pleasure for a long, long time. Even though I read interesting stuff, it's always kind of directed at gaining knowledge, because it's going to help me write about something else. So, for instance, right now there's a bunch of books. There's The Brief History of Intelligence. Have you read that book? It's by Bennett. I forget his first name. Timothy Bennett? Max Bennett? Yes. Wonderful book. And so, a lot of these things right now are still books that are somehow about questions about intelligence, and whether it's from the evolutionary biology perspective or from the perspective of technology. In terms of reading for pleasure, that I would have to literally go back 20 years, because there was a time when I would incessantly read fiction. So a lot of my writing, I think, or even the desire to tell stories, or even see stories in places where it's not obvious that there are stories, it has to have been informed by the fiction I read as a child, and through my teenage years, through my young adulthood. And we talked about this. John Steinbeck was a big favorite of mine.
Incidentally, what is your favorite book from Steinbeck?
A very, very unknown little book. It's called To a God Unknown.
Oh, really?
Yeah, not one of his
Not
well-known ones, but I highly recommend it. It's just an awesome book. Yeah.
Amazing. From literally quantum mechanics to machines, right? What made you gravitate towards this field, right? And since the talk is titled "The Future of Intelligent Machines," right? What does that phrase even mean to you, right? And how do you define an intelligent machine? And when we talk about future of intelligent machines, what comes to mind?
I mean, this is a huge debating point, right? I mean, what is intelligence? A lot of the sort of back and forth that goes on within academia and even in the research community is even trying to, figure out some pithy explanation for what intelligence is, and people disagree tremendously. But one kind of overarching way of thinking about intelligence is simply this adaptive ability that a system like us, for instance, has to use skills that it has learned, whether the skills are physical or cognitive, or the knowledge it has acquired, to use those skills adaptively to solve the task at hand, whatever that might be, right? And again, it's a very, very general definition, but when you apply that definition to, for instance, current AI, you'll immediately see that it doesn't actually fit the bill, as well as we keep talking about intelligence, but it's not intelligent in the way that humans are intelligent. So the future of intelligence is going to be about systems that can do exactly that, which as humans we do pretty effortlessly, right? We are very, very good at learning abstractions to solve a certain task, and then use what we have learned in order to apply it to a different problem in a completely different domain. AI researchers would call that generalization, and machines today don't generalize really well beyond their the training data distribution. We are continual learners, which is interesting given our what we've been talking about. Machines today are not continual learners. We are extremely, extremely sample efficient in terms of how much data we need to learn something. machines are not. The algorithms that we have right now are not. Yeah, and of course our intelligence is very embodied. And that definitionally speaking, intelligence doesn't have to be embodied, but certainly our intelligence is very much a consequence of us being embodied agents. Our intelligence is not just cognitive. There's an incredible amount of intelligence in every aspect of this body, right? And all of that comes together in our behavior and how we adaptively react to circumstances. So all of these things are various axes on which the future of intelligent machines are going to improve.
Interesting. You've talked about embodiment of learning, right? Especially for AI to even come close to what we call AGI, right? So maybe what does AGI mean to you, right? And how much and talked about the fact that the body itself is an intelligent machine, not only the brain, right? In some sense, like literally every part has a certain amount of intelligence built in. So what is to you, what is AGI today, right? And AGI as a frontier seems to be like a moving frontier, right? Where is that frontier possibly? Where's that horizon, if you will?
The interesting part is you just have to go back maybe 10 years, and if you had posited that there would be a machine like an LLM, right, people would have called that AGI. Right,
Yeah.
because it's one, and of course the goalposts have moved, not least because LLMs have limitations and they have other problems. But if you look at their sort of abilities, 10 years ago we would have been happy to call them some sort of general intelligence. In fact, LLMs are our first real example of things that have sort of capabilities that cut across sort of domains, right?
Mhm.
The same system trained on a whole bunch of sort of text data mainly, and also now multimodal data, is capable of being a mathematician, being a biologist, being a conversational partner, whatever. Like there's so many other things that come around. So you are seeing the first glimmers of generalized abilities. I still wouldn't call it general intelligence in the sense that these systems are not, intelligent in the way that we are, for all the reasons we just mentioned. So AGI, it's a moving goalpost. I think again, people struggle to definitionally pin it down, but you can think of it as a system that, keeping embodiment aside, would be able to do all the tasks that cognitive tasks that a human might, at the level of an above average human. So one system being able to do all the possible cognitive tasks that humans do, as well as an expert in the field. We're not there yet, right? And I'm sure when that happens, we'll move the goalpost even further, because there is something about embodied intelligence that these systems are not capturing. And that's a completely different research area, and intelligence built up literally from the ground up, where embodied agents are interacting with the world and learning about the world from their interactions. LLMs are kind of a top-down imposition of knowledge on these systems. So I actually weirdly don't fret about AGI in the sense of, there's somebody I'd interviewed for one of my stories, and we were talking about how will we know when AGI comes upon us, and his answer was, how do you know it's not already there, right? And whatever is the intuition you're using to say that it's not already there is exactly the intuition you will use to say that it's there. So there's almost no definitional thing here that it'll pass.
On that note, right, what do you think of the neuromorphic approach, right? In general, are you, yeah, do you think we are anywhere close to getting there, right? Because at some level, the brain chemistry and the physics around this has been well researched for almost a few decades now, right? And I'm not sure whether we've gotten even close to getting there, but and at times it feels that, and this is what we were talking earlier as well, right? That for me, neuromorphic almost feels like, hey, do we understand the brain, and can we reproduce it at a scale? And of course, and that is almost going back all the way back to Hoffield, and then there is something
even before, right?
Yeah.
I mean, so yeah, neuromorphic, I tend to think of it in a very specific fashion, but in terms of AI or machine learning having been inspired by our understanding of how brains work or how neurons work. I mean, that goes back all the way to the first neural networks in the 1950s, right? I mean, the first artificial neurons that were designed by people like Frank Rosenblatt in the late 1950s, they were essentially the first computational models of what we thought what biological neurons do, right? Brains, or our understanding of the brain, has always been an inspiration for AI. And even today, when people talk of the next breakthroughs that are going to happen to take us towards AGI, it's most likely going to come from ideas that are already there in computational neuroscience, because the kind of questions that AI is asking about, or people in AI research are asking about, how do we build these systems, exactly the same questions are being asked by computational neuroscientists who are trying to reverse engineer the brain. Where they're, we have an existence proof of a system that works, that is this 3-pound mass of brain tissue that is sitting inside the skull, that is an absolutely general purpose machine, right? uh, Again, in collaboration with the rest of the body. But reverse engineering that in order to understand what are the algorithms that are running inside biological neural networks, how does this accomplish all the things that we want to accomplish in artificial systems, there are ideas there. In terms of being inspired by how the brain works, yes, there's going to be a lot of stuff that is going to come. But very specifically in terms of neuromorphic hardware, I just think of it as hardware where you can literally run deep neural networks in hardware where the neurons are behaving more like biological neurons than our current artificial neurons do. Our artificial neurons right now, if you were to take an artificial neuron that is written in software and then have it implemented in hardware, it would be a equivalent of a neuron that is always on with some value, right? Biological neurons are not like that. They essentially produce spike trains of information. They spike at a certain point, and on average a given biological neuron is silent most of the time, and it occasionally, when its inputs have crossed some sort of threshold, it'll send out a voltage spike train on its axon. So that implemented in hardware would lead to enormous energy efficiencies, because a lot of the energy efficiency of the brain comes from the fact that our biological neurons are mostly not doing anything. It's the whole network that does a whole bunch of stuff, but an individual neuron barely consumes energy. So that implemented in hardware would be pretty amazing, and that has been done, not scaled up. But you also need to figure out how to build these systems first in software so that you can train these networks, and they are not trivial. So again, it has been done in principle, but scaling them up to the level of current artificial neural networks has not happened. But it's going to happen. I think it's coming.
I think that would completely change the entire, at least some of us who follow the entire data center economy and the power buildup that's happening around all of this is
possibly, yes. I mean, that's the biggest concern right now we have about the way AI is progressing, right? The enormous energy consumption that's happening because of these models. And if you had models that were running in hardware and were using orders of magnitude less energy, which in principle has been shown, not scaled up, but shown already. Yeah, that would change the economics of the whole thing.
We'll go back to the research part of this, right? I think the attention is all you need paper came in 2017.
2017.
Yeah, and uh, I have a question that, in some sense, and often there is enough press around this that the world has really not moved the frontier on research on this side, right? But I'm just curious on where do you believe the frontier for researchers today is, right? And what are the interesting areas of exploration for researchers out there?
I mean, there are quite a few. I think, maybe the perception that things haven't moved on is more from the side of the industry, right? I mean, yes, the industry took what happened with the attention is all you need paper, which was really as much an engineering breakthrough as anything else, because it made possible these very large scale engineering solutions to machine learning. But in terms of research areas, there's plenty going on. One would be neuromorphic hardware, and figuring out how to train these things called spiking neural networks in software, and that is progressing. That would be a huge breakthrough if it was possible to scale it up. Um, I think the other thing that has been quite sort of gaining traction is this idea that we need to build machine learning models that are capable of learning models of the world that the system is interacting with, and situate the agent within that model and use the internal models in order to make predictions about the world outside. This is something we think our brains are doing, and there's ample evidence that this is what our brains are doing. And so current systems don't do this, even though you can probe large language models and other vision models, etc., and discover semblances of these world models in the weights, but they're not kind of being used in the way we think our brains are using these models. So there's a lot of effort trying to build AIs that can learn these models of the world from the ground up, from their interactions with the environment, and then use those models to be able to interact and make predictions. One of the consequences of having world models inside is you suddenly can become much more data efficient. Like, think about yourself, right? Right now, if you were asked a question about something, you can run internal counterfactuals. Like, you can run through scenarios in your mind to
Yeah.
figure out, oh, what happens if I do this, what happens if I do this, etc., before you actually do something. So all of that is internal data generation that you're using to figure out the so you essentially start becoming more sample efficient. And also, what do these world models actually represent? So there's a whole bunch of research going on about the level of abstraction in which information is represented inside. You must have heard of this work that came out of Meta and Jan LeCun's lab, called JEPA, Joint Embedding Predictive Architectures. So those are addressing this idea that what we represent inside and what we use for prediction must be, for instance, if you're trying to deal with some vision problem, instead of predicting at the pixel level, you have to learn how to predict at this abstraction layer level, and that has enormous benefits. Um, there's also just stuff that's happening with large language models themselves, right? When you think of today's large language models, you have input comes in to the model. It's some text which is turned into high dimensional vectors or embeddings, and those embeddings progress through the transformer layers, so they're getting contextualized, and eventually those embeddings finally end up spitting out the next token or the next word. So you have this incredibly rich computation that happens inside the transformer, which is happening in a continuous vector space. And then it's turned into a discrete token, and then the whole thing is looped back, and you generate the next token, and so on. So you're wasting a lot of sort of computation that has gone on in very, very high dimensional sort of continuous vector spaces, by turning it back into a word, which is how we deal with language. And so there's research going on to let these language models kind of continue working inside these vector spaces before they turn things back into language. So this is called reasoning inside latent spaces. So that's a huge area of research. There's also energy-based models, which are probably going to be the next big thing. So, in the history of neural networks, when you talked of Hopfield networks are energy-based networks. They are inspired by physics and also the stuff that Hinton got the Nobel for, Boltzmann machines. Those are all what are called energy-based models, and they are not trained the way we train models today using backpropagation. And those things are inspired by the fact that there is something about the physics of the natural world where that is important for explaining why we learn at all. Why should any system learn anything, right? Fundamentally in nature, and some of that comes down to the thermodynamics of the system. And so there's a lot of inspiration
But
that
there's no like permanent stable equilibrium out there, right? So I'm just wondering that.
Yeah, so I think there is a yeah, absolutely. In fact, it's the in thermodynamically uh, or non-equilibrium systems, it turns out that self-organization is an imperative. Like because there is thermodynamic inequilibrium that you start getting self-organization to emerge, and self-organization becomes a very particular way of harnessing the energy that is flowing through a system, right? And once self-organization emerges, then it's in the interest of that system to maintain its self-organization, right? So a self-organization is a thermodynamic imperative, but once it emerges, then increasing complexity of self-organization becomes a self-fulfilling prophecy. So And therein lies the reason why things learn at all, anything about their world. It's essentially to harness the energy that is flowing through the system. And there are inspirations that are coming from that for machines.
Interesting. Uh, I think the other counter to this one is that the engineering fraternity, or the people who, if we talked about the empirical scaling laws, right? They took what we had at that point in time and have given us this magical world that we seem to be existing in today.
Yeah.
So I think might be interesting to get your point of view on maybe the arc from then to now, and for builders, because this a large part of this audience is actually builders, right? For builders, what are the frontiers which are possibly which possibly beckon them at this point in time?
I think in the immediate short term, the LLM scaling is not going to stop. I think we talked about the attention is all you need paper that kind of triggered this whole revolution. But there were parallel findings which are equally responsible for the scale of systems that we see. So in 2020 and in 2022, there were two separate studies, one by a team at OpenAI and another by a team at Google DeepMind, which establish these things called empirical neural scaling laws. And these laws essentially tell you that as you make deep neural networks bigger and bigger, more parameters, more neurons, and you train them on more data and you use more compute to train them, you can show that the loss that the network makes on test data falls predictably according to a power law. And these laws were established empirically, and they kind of provided the sort of theoretical incentive to argue that if we just made these LLMs much bigger and kept making them bigger, you would see them perform better and better on next token prediction, right? So all that it predicted was the error that it would make on next token prediction was going to drop predictably. Simultaneously, we were seeing that as these networks were becoming bigger, you started seeing emergent behavior, something that GPT-2 could not do, GPT 3.5 could do, even though the training and everything else about it is identical except for the scale. So this idea that behavior is going to emerge as things get bigger, and the fact that the scaling laws were telling us that if we just scale them, then the loss is going to keep falling in a predictable manner, and that falling loss then implies better behavior. These are the things that drove the current expansion of the size of LLMs, and that scaling. Uh, there's still considerable belief that there is more behavior left to wring out of the scale, right? And also the initial scaling laws were for the compute that was used during pre-training. And subsequently, what has happened is we have realized that we can also use compute for fine tuning a large language model. After the pre training is done, when you use things like RLHF or supervised fine tuning, etc., those are post the pre training phase. And there's compute that you can put into that phase. And that is also allowing you to scale up your system's capabilities. And something that is even more dramatic that has happened in the last year is providing more and more scaling of compute during inference. So when a large language model is basically answering a query, adaptively using more compute during inference, so that it is able to say that, oh, if the problem is hard, it's going to use a certain amount of compute, but if the problem is easier, it'll use much less compute. Adaptively scaling the compute on the inference during inference time. So all of these things have shifted the scaling law curves. We don't have empirical sort of formulations for these new scaling laws, but I think people still believe that there's a lot to wring out of scale, which cuts both ways. It also means that these data centers are going to get bigger and more energy hungry, and all of the problems that are associated with that remain. But in terms of founders, I think so I would say there's still a lot to be gained by paying attention to what is happening in the LLM space.
Got that. I think we'll talk a bit about the book. There's a good part of the book. While you do say that if you know high school math, it's fairly accessible. But yeah, I have done high school math, and when I was reading it, I I realized that it was not as accessible as you made it out to be. But so the question here is that you chose math as a language to kind of explain this. Of course, there's a lot of interesting stories in there as well, and we'll touch upon that part as well. Why did you choose the mathematical underpinnings when you wanted to talk about it? And when I was started reading this, and this possibly you might have got this question earlier as well, right? Just from the title of the book, right? I was like, hey, you know what? Why this is almost like how machines learn, right? Why is this even why machines learn, right? So I started. I think maybe the dissonance started there. So I'm just curious on both why using math as the language to explain this, and B, why the title, why.
Yeah, absolutely. Good. So I think for me, the machine learning journey began without any intention of wanting to write a book. I think it was simply my effort at wanting to understand this technology. And I think I still remember when I was a software engineer, I had come across a popular science book called Neural Networks. And I read a little bit of it. And I remember thinking, oh, this I would want to work on. Never followed it up. And I still think that if I had actually persisted with it, and far back, I probably would have continued in software. But anyway, that never happened. And so this whole effort now was just kind of interest, right? I started learning the math, and there was, I still remember one particular proof that I was trying to understand, and it's called the perceptron convergence proof, right? And the perceptron is the first single layer artificial neural network that was designed in the late 1950s by Frank Rosenblatt, who was a Cornell University psychologist. And so, the algorithm was there. It's a very, very simple algorithm. It's a linear classifier. And 1958, he builds the system, it works. And within 2 or 3 years after that, people started figuring out mathematically why that algorithm works, right? So the how was the algorithm in my mind. And it was the mathematical proof of the algorithm's workings that provided the rationale for saying, okay, here's why this algorithm does what it does. So it's the conceit of a writer. Honestly, you can easily argue that it should be how. And in fact, I still remember an interaction with this was a event that Mukesh Bansal had organized, where there were a couple of Nobel laureates, physicist
Of
David
course, the
Gross.
ICTS one. Yeah.
Yes,
Yeah.
in Bangalore. And so I was trying to explain this exact same thing to David Gross. He's a Nobel winning physicist. He just would not buy my rationale. He said, no, that's still how. There's no way this is why. And he's right. Why is it has to come from physics. If a machine has to learn something, the real why is because there is a thermodynamic imperative for it to do what it does.
Same
And
word.
so, it's essentially, again, if a system is self-organizing for whatever reason, and then it is doing whatever it needs to do to preserve self-organization, which implies learning something about its environment, etc. The learning begins at that stage. It might be just a single cell. So, but that is a physics imperative, and that's the real why. And that's a much harder question to answer. So this is my conceit, basically.
Nice. And for builders, right, and often uh, given what many of us are doing there, right, one of the frontiers is explainability, right, and on what are you able to build something which is consistent and gives a certain kind of experience, and B, how do you interpret the constraints slash opportunities which are available therein, which is all of us playing with the infra being created today.
Say a bit more about the question. I
So,
mean, like what?
I think just things that we're putting in front of users, in front of our users and customers, right? Often uh, one of the constraints that many of us do struggle with is that there's a bit of erratic nature to what is being thrown out by whatever we built.
Oh, I see.
Right. So
Yeah.
there's we could call it hallucination, or just the underlying model changes, and often you're trying to bring the performance of your product back to where it is. So one is how do you possibly do a better job of understanding yourself that this is what is at play, and B, the frontier of explainability itself on possibly leveraging the opportunities that might be therein.
So the first thing, in terms of why these systems change from, let's say, generation to generation of models within a single company or from across companies, That, in fact, that is the rationale for why I wrote this book, for instance, right? Even though I started this well before the LLM craze began, my contention is that if you really want to understand why machines are doing what they're doing, you need to see the math for what it is, right? So it becomes very, very clear when you look at the math of large language models, right, that every instance of an LLM will have different behavior. It's a probabilistic system, and it is learning what are called conditional probability distributions over data, and the shape of the distributions that it learns and samples from is going to be different depending on the size of the model, the amount of data you use, the nature of the data you've used, the quality of the data, how much compute you've given for training. The more compute you have, the more data you have, the the shape of those surfaces, probability distribution surfaces that it learns, can be much more complex. And so once you see that for what it is, the fact that every sort of instance of an LLM will have slightly different behavior is not a mystery at all. Of course, that will be the case. So you have to engineer around that, or keep that in mind when you build your products. In terms of explainability, I mean, that has a very particular meaning in neural network research or machine learning research, right? Trying to understand why a system is making the decisions it's making, or why it's doing what it's doing. And neural networks are famously difficult in that sense, right? All we have are the weights of the model, and it's very, very hard to reverse, except in very small systems. It's very hard to reverse engineer what the model has learned in order to do what it's doing, right? So explainability at the level of trying to figure out the inner workings of the model is still a big research area. How you would leverage that for your audience, I mean, for the people who are going to use your systems, I think those are that's I think as a
Orthogonal areas.
yeah, it's a difficult problem. I think as a builder, you just need to be aware that you're going to get a lot of variation in these models, and you have to be very careful about engineering your solution so that for the user, there's some sort of standard that is maintained in terms of the experience.
Uh, you know, we are at South Park Commons and we have a lot of founders in the audience. And, you know, of the entire journey around the way AI has developed over a period of time, I believe one of the most fascinating parts of the entire story is just the sociological side of it, right? The fact that a lot of people were in the wilderness for a while, right? And of course, you talk about Rosenblatt, but after after the book Perceptron itself, right, by Minsky, it seems that there was almost like a scorched earth by way of both talent and funding in the space, and and often it feels like the founder's arc, right? That you're onto something, and almost everybody is questioning you on why are you doing this, right? And often you stand out like a sore thumb. And I often wonder what was the motivation of people like Hinton or Hoffield, and I know we talked about a bunch of others, right, who kind of pushed the field forward for decades altogether.
I think maybe the story of sort of the first AI winter is illustrative of what happened. So we talked about the perceptron. This was late 1950s. These were single layer neural networks, and very soon after, we had mathematical proof showing that these single layer neural networks do an amazing job, and they will do an amazing job if there is a solution to be found. Marvin Minsky and Seymour Papert wrote a book called Perceptrons in honor of Rosenblatt, in which they have a lot of mathematical stuff. And one of the things they prove in that book mathematically is that single layer neural networks will not solve some very, very simple problem. It's called a XOR problem. And essentially saying that if there is a nonlinear boundary that needs to be found in order to classify data, then this won't work. And then they kind of insinuate, without mathematical proof, that multi-layer neural networks will also not be able to solve that simple problem. And I remember, so I interviewed Jeff Hinton for this book, and I remember starting that, very early in the conversation, I mentioned this Minsky and Papert proof of sort of multi-layer neural networks. And he immediately said, we'll talk about that. I reserve the right to complain about that. So, so he was a PhD student when all this was going on. And while the rest of the industry kind of took Minsky and Papert at their word, he didn't. He said he's completely wrong. That is just, he's basically conning people. Minsky and Papert are conning people, and they had their incentives. Minsky and Papert were much more interested in symbolic AI, the other competing way of doing AI for a few decades. So funding was being apparently redirected towards that. But people like Hinton, there were very, very few who saw the end game pretty clearly, except that the steps from where they were to the end game was not at all clear. There were lots of small things that had to change in order for them to be able to build and train multi-layer neural networks. But he persisted. He refused to give up because he was convinced Minsky and Papert were wrong. B, he was convinced he was right, which in hindsight he was. But it was simply dogged persistence. He just would not let go of neural networks, right, for a good 20 years. While there must have been just 10 people worldwide who are even thinking about this with any great intensity.
I often wonder about the reward function out there, but
Yeah.
yes, interesting.
Yeah.
Um, let's talk about a bit of limitations of AI, right? And many of us who believe in the promise, right? In what areas or domains do you expect AI to continue remaining inferior to humans, right? And there are times that all of us just wonder that, hey, this seems to be both magical, and we use the word scary in a previous conversation like multiple times, right? So what are the areas where you expect this to remain inferior?
So this question, there's a lot of it depends on what we think human intelligence and consciousness is, right? If you take a materialist perspective about what we are, which I do, then we are also just machines, albeit extremely sophisticated machines, right? And that our intelligence and our consciousness and our sense of self, etc., are the outcome of computational processes, right?
Sure.
So A, we have to assume materialism. B, we have to assume that everything that we are is an outcome of computational processes. And C, we have to assume that computations that are carried out in substrates other than biological substrates will also lead to the same phenomena, right? So because in AI we are implementing these computational systems in silicon, they don't have the same properties as biological systems. So if you make those assumptions, if reductionism is right, if materialism is right, if everything is an outcome of substrate independent computation, then there is no in principle reason that we can't build machines that will be like us or even exceed those capabilities. So currently, yes, all those things that we talked about earlier, the ability to generalize, lack of continual learning, being extremely sample inefficient and requiring enormous amounts of energy and data to learn whatever we are learning, not being embodied, and the consequences of that. All of these things are where AI is lacking today. But if those assumptions that I just mentioned are right, there is no in principle reasons for us to get build machines that will also get there. Whether that happens in the next 5 years or 20 years is anybody's guess.
Yeah. Given what Jan LeCun said maybe yesterday, right?
He keeps saying quite
Yeah.
often these days, yes.
So just curious that, right, both learning and intelligence, and in some sense, even the other part is consciousness and creativity, right? So if we extend the same argument, right, can AI actually be fundamentally trained beyond the data sets and beyond the logical constructs that it has been exposed to?
It's the same answer. Think about it this way, right? Again, assuming materialism is correct, right? And that there is nothing external to us apart from the matter that we are composed of, then this machine has come about because of millions of years of evolution in which billions of nervous systems have interacted with the environment and learned whatever needs to be learned for the organism to survive. So this is a machine learning system, right? And so we have existence proof of a biological machine that can arise by simply interacting with an environment, learning about patterns that exist in the data that it is encountering, using those patterns to then make decisions about what the organism needs to do to survive, etc., etc. So, and it has come to a point where it has not just evolved to recognize patterns, it has evolved sort of architectural details that are part of our brain, and it has figured out algorithms for learning which we haven't yet deciphered, right? Our brains are not doing back propagation, right, in order to update the synaptic weights, but they're doing something that is akin to, it's achieving the same goal, but it's doing something much more efficiently. So we have an existence proof of the fact that it can be done. And given that it can be done, this system has creativity, has all the things that we consider human.
Yeah.
But if it's in principle possible to have a machine get to this point just by interacting with data, which is the outside world, again, no reason why machines shouldn't get there.
Sure.
We just don't know what those algorithms are. We just don't know what those architectures are yet.
Sure. Yeah, no, I think the temporal axis that this system has taken to get to this point, hopefully this system can architect something that gets to that point sooner and faster and more efficient way.
Possible, yeah.
Yeah. We'll at this point in time, we'll get a little personal here, right? A few rapid fire, right?
Oh dear. Okay.
Yes.
You
So,
didn't tell me this before.
this is the surprise element of this chat. So how do you use AI in your daily life and work, writing, whatever else?
So I've talked about this before with others, where I don't use AI for my writing.
Mhm.
And the reason for me for that is very simple. Writing is what gives me meaning, like my life meaning. I do not want to use an AI for doing something that is very meaningful to me. Saying that, I do use language models for learning about matrix math, or diffusion dynamics, or whatever that might be that I need to figure out, which would have involved looking up a textbook or some other research source. But now LLMs have become an extraordinary sort of tool for learning, very fast and very targeted learning. So I do use it for that. I will not use it for writing. Somebody else might use it for writing, because writing for them is not what constitutes, is not meaningful to them in the same way that it is to me. Like if you were to ask a visual artist whether they would use a vision model or a generative vision model for generating images, they would be aghast. They'll say, how can you do that? I personally have no problems, generating cartoons using, LLMs, because I'm not an artist in a visual sense. So that I can't draw for nuts. So I'm quite happy to use that. So I think it'll come down to each one of us. The things that we find meaningful about our lives, hopefully we'll hold on to that and not use AI for that, but use AI for other things that augment that pursuit, whatever that might be. So yeah, if you're a software engineer, for instance, right? I mean, there is a certain joy, and I know this from having been a software engineer. There is a certain joy in knowing the insides of a piece of code, right? If you give away that ability to an LLM and you never really know how to code, you've lost something. It may not be important to you. That's okay then. But if it is, then I would say don't give it up.
Sure. You, of course, meet a lot of people who are leveraging AI in multiple form factors, right? So, what are the common pitfalls or misconceptions that you see when you're talking to people out there
About AI?
about AI?
I think probably the biggest misconception that people have about AI is it's some sort of monolith, that there's one thing called AI, and of course there isn't, right? Even over the course of the history of AI has meant different things. Very broadly, it has either meant symbolic AI or it has meant machine learning. And within machine learning, all of you know that there is no one single machine learning model that does everything, right? All sorts of things are going on. So I think the biggest misconception would be that there is this thing called AI, and some of it is just brought on because of the success of ChatGPT, literally that one model, right? The other thing I think that where I think it really helps to get under the mathematical skin of all this is thinking about AI as not realizing that these are inherently probabilistic models. So are we as humans.
Mhm.
We tend to think that when we make decisions, just because we feel internally 100% confident that somehow that decision is 100% correct is completely mistaken. You can be 100% right about something internally, which could be completely wrong in terms of the actual outcome. Machine learning systems are no different. They are probabilistic. There's an inherent risk of error in every machine learning system. There's a lower bound to how low that risk can get. There's always going to be that. And realizing what that is, I think, is really important when you design systems, because you have to account for that, right? Anything that you're going to build has to account for the fact that these are probabilistic systems.
Yeah.
So I think those two would be the big overarching misconceptions about AI.
Nice. And what when we talk about the future of intelligent machines, right? What are some developments that you foresee, that you are personally excited about?
I think for me, the most exciting thing is the inspiration that is being drawn from current models from computational neuroscience. Right, computational neuroscience have been struggling for a long time, and I have already have sophisticated models of how our brains do what they do. Right, even if you take something as I was going to say something as simple, but not, it's not simple, like vision, right?
Yeah.
Our vision, like when you're perceiving something from the world outside, there are photons that are hitting our eyes. An image is forming on the retina, and the traditional account of vision would have involved that image sort of being processed from the bottom up, right? You have pixels are turned into edges and shapes and colors and more sophisticated features, and then you combine that to say, oh, I'm looking at a camera or something, right? It turns out computer vision tried this approach for 30 years and they didn't succeed. This is not, and neuroscientists have known this for 150 years, that this is not how the brain could possibly be doing vision, right? So there has been this entire approach in neuroscience about something called predictive processing. This idea that there are layers of processing going on in our brains. The uppermost layers are the most abstract. They have these things called world models. They use the world models to be able to predict what the layer below should be seeing, and that layer then predicts what the layer below should be seeing, and you go all the way down to the senses, and the lowest layer of the neural networks are telling the eyes, oh, we think that this is the information that should be entering the eyes. If that prediction is correct, it means that the hypothesis that the topmost layer made about what is out there is correct. What you perceive is the hypothesis always, right? And if there's an error in the prediction, then that error propagates up and the world models get updated. And this is a architecture that is now playing out in research labs, where we are seeing AI systems that are beginning to because this involves recurrence. These neural networks are extremely hard to train, right? They're all recurrent neural networks. The current neural networks that we have are all feed-forward networks, artificial ones. But the biological ones have huge amount of recurrence built into them, and very hard to train, extremely intense training procedures. So, but we're beginning to see, I think, the stuff that comes out of these ideas are probably going to be on the right track.
Yeah, this indeed is exciting. And what is it that about the future of AI kind of keeps you up at night?
I was having this conversation with the professor at Berkeley
Mhm.
a few months ago, and we were both saying that we're kind of happy that we are at the end of our careers, that we don't have to deal with the consequences of all this, and we can just partake in the joy of this stuff. And I can see lots of young faces here, and it's I mean, it is worry. It doesn't worry me personally, like I said, but I think it is worrying in terms of the consequences this is going to have for society. I think there is a crisis of meaning that is going to come, right? We find the meaning in our lives in what we do and how well we do that. And especially when it comes to cognitive tasks, a lot of these cognitive tasks are eventually going to be done by these machines. And for those of us who find meaning in our lives in doing these cognitive tasks, whether it's coding or whether it's writing or whatever it might be, I think there is a crisis afoot. So that would be, I would say, keep that in mind. And I don't know how. I don't think there's a single solution here as to how you deal with it. I think as a society, we have to figure out how to deal with this, but it's coming.
Yeah. No, that's a very sobering thought. The activation energy to get to your personal meaning is going to go up significantly. But thanks a lot for sharing that perspective. With this, we'll turn it over to the audience, right, for questions. Okay.
So, hello, can you hear me? Perfect. So, this is some experiment I am doing. So, what is that one question that you can answer, which we cannot find on internet? Like the answer we cannot find on internet. Like, is there any question which you can specifically answer?
Oh dear. As a writer, very unlikely that I have something to say that you cannot already find on the internet. Um, not really. I think it would be really arrogant of me to say that I have something to offer you that you can't find out there. I mean, one of the things about being a science journalist and science writer is that you are researching what others are doing, understanding it, synthesizing it, and then telling stories about it. So, in some way or the other, everything I write about or what I know is already out there. My skill is in trying to make stories out of it and making it understandable to the general audience. But if you are willing to put that effort yourself, the information is out there.
Hello. Hey. So I want to ask you about the Richard Sutton's like the bitter lesson, which he basically says that everything after a certain scale, everything sorts out, nothing else matters, right? So and he says everything's gonna like sorted out as part of RL, right? What is your take on it, and how much of that RL is because of evolution, and how much of is as part of like your humans' life of learning throughout? Like how much do you think RL plays a role versus imitation learning, and how much? Yeah.
I don't think we have kind of delineated in the context of a human being how much of it is RL, how much of it is imitation learning. All of it, all of it is part of what we are, right? And we don't even take into account that it's not just a single human lifetime here. That's the question, because if you look at your brain, it comes with what in machine learning would be called inductive biases, right? The convolutional neural networks that we designed in people like Jan LeCun, etc. Those were inspired by what we understand about our visual cortex, and this visual cortex is the outcome of millions of years of evolution. So there's a lot of inductive bias already baked into. Some of that is going to be the consequence of RL over evolutionary time, right? That individual neural systems that have encountered things in the environment. So I mean, this is a hard one. I don't think. I think scaling still remains sort of engineering technological solution, because that's the least sort of I guess in terms of when it comes to companies making bets on how to go forward, that's probably the least problematic, right? They know that if you just scale up, you're going to get something out of it, and then you keep your fingers crossed, saying, okay, something magical will come out of it. So far, magical things have been happening. How far that goes is anybody's guess. But my suspicion again is that we are a few breakthroughs away. Just like the attention is all you need paper we talked about earlier, some breakthroughs that are going to be inspired by neuroscience, papers like that might change the game again, where scaling might not be the answer, where some other architectural change that would be the key. So I don't have a crystal ball to tell you how. This is just a guesswork here.
Hi, I have a really tactical question. So, you're a writer, you've spent decades perfecting your craft, and you said you don't use AI for writing, but a lot of us do. So, do you have any concrete steps that we should take so that our AI written writing doesn't sound cringe?
uh, well, again, it depends on what you're, why you're writing, right? I mean, if your writing is in the context of a company where you're just trying to communicate ideas to each other, then using AI seems perfectly fine. But at the same time, uh, if you don't have the innate skill to, like, how do you know that it's cringe, right? That itself is a learned skill. Most people won't even be able to tell that it sounds horrible, right? Because that's all they've been exposed to. So I would say just do what almost every writer has done before you, which is to read good stuff. Read old literature. Don't read literature that is coming out in the recent passed because who knows, they might have used AI for it. But read the grades from decades ago, and your brain gets wired. Your brain get just like we are wiring up large language models to learn the syntax and semantics in human written language. Our brains are no different. You read enough, and your brain starts seeing good writing from bad writing.
Yeah, absolutely. Classics are classics for a reason. Yeah. Yeah.
He said.
You mentioned that intelligence is substrate independent. Do you think it is also distributed? There's some kind of a hive mind and like flock of bird and ant hills and all. Some people speculate that. What's your take on that?
I'll tell you a very concrete result that came out about probably a few months ago now, that they showed that if you take this was a study that was done specifically with honeybees. I mean, they were not working with honeybees, they were using computational models of honeybees where the individual interaction or the individual behavior of a honeybee is very simple. And they showed that the emergent behavior of a swarm of honeybees has the same mathematical properties of a reinforcement learning agent. That was the whole thing. The swarm as being the agent that is being trained using reinforcement learning, whereas the individual agents were very simple. So yes, so there can be emergent behavior from the I mean, hive mind is not something magical, right? Hive mind is simply this idea that, so I'm still within the confines of physical systems, right? Everything is still happening according to material systems interacting with each other through material means. There is no magic outside of matter and the interactions of matter. Nothing?
Sorry, one question, one person. Yeah. Tushar, you want to go?
Yeah. So you mentioned that we are also probably trained how machine learning models train models, and we've been trained over data over centuries, etc. Do you think that's an absolute truth, or is that an assumption we want to operate with, such that we're able to, let's say, start picking data that we want to be trained on?
I'm not sure I understood your question. So say that, so you're talking about humans?
Yeah, I'm talking about humans.
Yeah.
A lot of models get inspired from how our neural networks work. But you said that probably we also have trained on data over centuries and thousands of years. Do you think that's an absolute truth, that we also get trained over data the same way ML algorithms train? Or is that
So
an
your question
assumption?
is human learning fundamentally different from the way machines learn?
Yes.
And yeah.
And what if some proportion of us learned the way we are making machines learn today, what proportion is that, if at all it's a proportion?
I'm not sure we have any way of quantifying that proportion, but the idea that, again, remember I talked about certain assumptions you have to make about this argument that we are materialistic systems, right? That there is nothing outside of matter in the functioning of our brains and bodies, and that our intelligence, etc., can be reduced to computations that are happening in the system. If that is the case, and that's a big if, there is still, even though most neuroscientists and philosophers, etc., will more or less agree with this, there is enough dispute about these assumptions. So if these assumptions are correct, then there's hardly any doubt that nervous systems over the course of evolution have encountered data. Where else are they going to learn anything from? Unless, that's why I'm saying, if you don't posit some external thing that is teaching these things, like just we are building machines, and we are at this point using supervised learning to train the machines. Then we went from supervised learning to self-supervised learning. So, in biology, that's what would have happened, right? Biological systems would have been using some form of self-supervised learning to learn about the world, the abstractions that are necessary to model the world outside, and use that learned sort of knowledge to then act on the world and survive and procreate and all of that, right? If those assumptions I made about materialism are correct, there is really no other way to explain other than the fact that these are biological machines that have learned using some form of self-supervised learning, and have not just become machine learning systems, but they have evolved algorithms to learn effectively. All of that is happening, right? I don't think there's any given those assumptions, I don't think there's any doubt. If that assumption is wrong, if there is something other than matter in the way we function, then all bets are off. And we have no idea what that might be.
Sure.
Yeah.
You have two last questions to the lady. Okay.
Hi, I'm Atul, and given your background in electrical engineering, I wanted to ask what do you think are the scope and challenges of AI in this domain and in electrical and electronics domain? Second question is
Okay, one question per person. So
Okay,
we'll hold you there. Yeah.
Scope and challenge of using AI for electrical, and I mean it's the same for any engineering. Anything that you might want to do, right? I mean, fundamentally, I think what machine learning and AI has done is it has changed the way we have to think about problem solving. Especially for me, this was very clear because I used to do software in a certain way, and then there was a 20-year gap, and then suddenly I encounter machine learning, and for those of you who, a lot of you are young enough to have been weaned on machine learning, so you don't even realize that there was a very different way of doing software. So I think doesn't matter whether it's electrical engineering, civil engineering, there is a problem to be solved. Traditionally, you would have taken that problem and you would have decomposed that problem into its constituent parts and written code or whatever, the math to solve that. Now it's about saying, okay, how can I think about this problem in machine learning terms, which is figuring out what is the data that I can collect and what are the questions I can ask of the data in terms of the patterns that are inherent in the data in order to solve the problem that I'm wanting to solve. So it's just a flipping of the way you think about problem solving. All, regardless of the type of engineering, I think all of them are amenable to machine learning.
Hi, sir. So I'm here.
Where? Oh, okay.
So you are who I would consider a polymath in the sense that you're curious about various things in various fields. So I wanted to ask, how do you keep up with all of this without getting overwhelmed with everything new that comes your way?
Well, first, like I said, make sure that your ability to pay rent depends on learning. So then that really helps. But I think it's stuff that happens over time, right? At any moment in time, every story that I'm trying to write feels overwhelming, right? So like if I go back 20 years, the first stories that I was writing about cosmology and writing stories about dark energy and dark matter, they felt difficult, right? But you persist. And then you write 20 of those stories and suddenly you have, it's just emergent knowledge in your own neural network. So somewhere things start clicking. And so one of the good things about writing articles for magazines, etc., is that you also have to learn about how to spot the essence of a story. Learn enough that you can make the story consistent. That in the confines of a 400-word story or a 2-page story, that you have learned enough to keep your logic consistent. There might, and the reader doesn't need to know that outside of the confines of that story, you actually don't know a whole lot, right? But over time, as you write more and more and more and more of these, suddenly the way you write stories, the kind of stories that you write, they just start becoming more nuanced. They may not, like when I look back up to my earlier stories, I know they were not nuanced. The reader may not realize it, but you know that. So I think it's just persisting with it.
Cool. We'll have to stop the questions, but maybe Anil might spend a little more time with us for a few more conversations. But I do want to say this is one of the most, but just by the way of intellectual stimulation, this talk was way off the charts. So,
I'm glad.
So thanks for doing this, and thanks for being so generous with your time.
My pleasure.
Yeah.
Thank you for having me.
Yeah, and thanks for writing the book. The library at SPC has a copy of the book, and the team asked me to get a signature. Right? Yeah, you can possibly. I'm going to hold your mic. Yeah, there you go. Yeah, or you can just write, keep learning. Yeah. Keep exploring, yeah. There you have it.
20 years ago, I bought a North Face backpack that had the tag, keep exploring. And that backpack has been with me all the way to the South Pole.
It's a classic. Thank you.